The container ship Ever Ace, one of the largest vessels afloat, stretches 400 meters long, a length greater than the height of the Empire State Building. Loaded with 24,000 TEU containers, it displaces more than 230,000 tons of water. This colossal mass, once in motion, seems unstoppable. Yet, buried deep within its hull, an engineering marvel provides the precise, controlled power needed to overcome the ocean's immense drag and propel it across continents. This unseen heart of the ship is a single, immense diesel engine. Specifically, for the Ever Ace and its sisters, it is likely a Wärtsilä-Sulzer RT-flex96C, one of the most powerful and gargantuan engines ever built. This engine's pistons are nearly a meter wide. The cylinder bore is 960 mm, roughly 38 inches across. The engine stands more than 13 meters tall, taller than a four-story building, and weighs over 2,300 tons. When it runs, the crankshaft, a steel beam thicker than a man's torso, rotates at an astonishingly slow pace for an engine of its power. You might expect an engine designed to move the largest ships on Earth to roar at thousands of revolutions per minute, like the engine in your car. Instead, this behemoth turns at less than 100 revolutions per minute. At full power, it might lumber along at 80, or perhaps 102 revolutions per minute. Why does the world's largest diesel engine run at such a seemingly glacial speed? Why isn't it designed to spin faster, to generate more power with quicker pulses? The answer, like much of heavy engineering, lies in a delicate balance of physics, material science, and the relentless forces of inertia and heat. It's a riddle that, once solved, reveals the extraordinary ingenuity hidden within the machines that underpin global trade. By the end of this journey, you will understand the precise engineering trick that allows these giants to move mountains of cargo at a pace that seems to defy their own fundamental design. First, let's consider the sheer scale of the components involved. The pistons, as mentioned, are 960 mm in diameter. Each piston has a stroke, the distance it travels up and down within the cylinder, of 2,500 mm, or 2.5 meters. Imagine a cylinder nearly a meter wide and over 2.5 meters deep. When the engine is running at 100 revolutions per minute, that means each piston travels up and down 100 times every minute. In each revolution, the piston moves down 2.5 meters and then up 2.5 meters. That's a total travel of 5 meters per revolution. At 100 revolutions per minute, each piston is covering 500 meters of travel every minute. This translates to a piston speed of 500 meters per minute, which is 8.3 meters per second. Now, 8.3 meters per second might not sound incredibly fast in the abstract. However, consider the mass and forces involved. Each piston, along with its piston rod, crosshead, and a portion of the connecting rod, represents a significant moving mass. This entire assembly accelerates from zero velocity, reaches its maximum speed at the midpoint of the stroke, and then decelerates back to zero at the end of the stroke, before reversing direction. This constant acceleration and deceleration generates immense inertial forces. The critical constraint for these engines is something called mean piston speed. Engineers have determined that for these colossal engines, the mean piston speed must be kept below roughly 8 meters per second. The RT-flex96C, with its 8.3 meters per second, is pushing that limit. Why is this limit so crucial? The primary reasons are liner wear and connecting rod fatigue. The piston moves within a cylinder liner, a replaceable sleeve that forms the combustion chamber. Despite sophisticated lubrication systems, there is still friction between the piston rings and the cylinder liner. The faster the piston moves, the greater the velocity of rubbing friction. This translates directly to increased wear on both the piston rings and the cylinder liner. Excessive wear shortens the lifespan of these critical components, requiring more frequent and costly overhauls. Given the sheer size and cost of these parts, preventing premature wear is paramount. A single cylinder liner for an engine like the RT-flex96C can weigh over 5 tons and cost tens of thousands of dollars. Replacing it is a major undertaking. Beyond wear, there's the issue of dynamic stress on the connecting rod and other reciprocating components. Each time the piston reverses direction, the forces of inertia attempt to tear the connecting rod apart or compress it. At the top of the stroke, as the piston decelerates and reverses, the tensile forces are immense. At the bottom of the stroke, as it reverses again, the compressive forces are equally powerful. If the piston speed were to double, the inertial forces would quadruple because force is proportional to mass times acceleration, and acceleration is proportional to the square of the piston speed for a given stroke length. These forces would quickly exceed the material limits of the steel components, leading to fatigue cracks and catastrophic failure. Imagine swinging a heavy sledgehammer. If you swing it slowly, the forces are manageable. But if you try to swing it twice as fast, it becomes exponentially harder to control, and the stresses on your arms and the handle multiply dramatically. The same principle applies to these engines, but with components weighing hundreds of kilograms and moving with the energy of a small car crash hundreds of times a minute. So, if piston speed is the limiting factor, why not simply reduce the stroke length to allow for higher revolutions per minute? If the stroke were half a meter instead of 2.5, the engine could theoretically spin 5 times faster for the same mean piston speed, generating more power from a smaller footprint. This brings us to the core engineering trick, the massive stroke-to-bore ratio. The Wärtsilä-Sulzer RT-flex96C has a bore of 960 mm and a stroke of 2,500 mm. This gives it a stroke-to-bore ratio of roughly 2.6 to 1. This is an exceptionally over-square, or long-stroke, design, especially compared to high-speed automotive engines, which are often under-square, with a larger bore than stroke. The long stroke is not a weakness, it is a fundamental strength, deliberately engineered to extract maximum work from each combustion event. To understand this, we need to talk about the physics of combustion and expansion. In a diesel engine, fuel is injected into highly compressed, hot air, igniting spontaneously. The rapid combustion creates extremely high pressures within the cylinder, pushing the piston down. The longer the distance the piston can travel while being pushed by this expanding gas, the more work can be extracted from that combustion event. This is where the long stroke shines. Imagine a single combustion event as a powerful, controlled explosion. The pressure exerted on the piston drives it down. If the piston only travels a short distance, a significant amount of the energy of that explosion is still contained in the hot, high-pressure gases when the exhaust valve opens. This wasted energy is released into the exhaust system as heat, rather than being converted into useful mechanical work. By allowing the piston to travel a much greater distance, the gases have more time and volume to expand, reducing their pressure and temperature before they are exhausted. This process is called expansion work. The long stroke maximizes this expansion, making the engine incredibly efficient at converting fuel energy into rotational energy of the crankshaft. It's similar to stretching a powerful spring. If you only let it expand a short distance, it still holds a lot of potential energy. But if you let it expand fully, it releases all its energy as work. These marine diesels are designed to be the ultimate expanders. They are built for extreme thermal efficiency, which means getting the most possible mechanical power from every drop of fuel. Fuel consumption is a critical metric for shipping companies, directly impacting operational costs and profitability. A typical RT-flex96C consumes roughly 171 grams of heavy fuel oil per kilowatt-hour. For an engine producing over 80,000 kilowatts, that's a staggering amount of fuel saved over thousands of operational hours. Which of these machines would you least want to be standing next to? Tell me below. Another critical factor contributing to the low RPM is the two-stroke cycle these engines employ. Unlike four-stroke engines, which require 2 full revolutions of the crankshaft for each power stroke, two-stroke engines complete a power stroke in every revolution. This means that for a given RPM, a two-stroke engine produces twice as many power strokes as a four-stroke engine with the same number of cylinders. This effectively doubles the power output per cylinder for a given engine speed. Consider a 14-cylinder RT-flex96C. At 100 revolutions per minute, it is delivering 1,400 power strokes every minute. If it were a 4-stroke engine, it would need to spin at 200 revolutions per minute to deliver the same number of power strokes. But as we've established, higher piston speeds mean higher wear and stress. The 2-stroke design allows these engines to generate immense power and torque at very low rotational speeds, adhering to the piston speed limitations while still achieving colossal output. The slow speed also plays a crucial role in enabling the use of heavy fuel oil. Marine diesel engines typically run on bunker fuel, a thick, tar-like residual product from oil refining that is far cheaper than the refined diesel or gasoline used in cars. This fuel is so viscous it must be heated to over 100 degrees Celsius just to be pumped and injected. The slow engine speed provides more time for fuel injection, combustion, and the complete burning of this dense, difficult-to-ignite fuel. Faster engines would struggle with complete combustion, leading to inefficiencies, increased emissions, and fouling of components. The long, deliberate combustion cycle ensures that nearly every bit of energy in the heavy fuel oil is extracted, another testament to the thermal efficiency driving the design. So, the common-sense guess, that a powerful engine must spin fast, is precisely what engineers avoid at this scale. Everyone assumes high speed equals high power. Here, the engineers do the exact opposite. They deliberately design for slow, deliberate motion. The trick is not raw speed, but rather maximizing the expansion ratio and power strokes per revolution. The slow RPM is not a limitation, it is an engineered feature, a consequence of optimizing for efficiency, durability, and the use of the most cost-effective fuel available. The result is an engine that moves with a rhythmic, almost hypnotic slowness. Each monumental push of the piston is a testament to controlled power, a carefully managed explosion extracting maximum energy. The massive crankshaft turns with a ponderous grace, its rotations echoing the deep, patient pulse of the ocean itself. This slow, deliberate movement is what keeps the piston speed below the critical 8 meters per second threshold, minimizing wear and preventing fatigue. It's what allows the long stroke to wring every last bit of expansion work from the combustion event, and it's what enables the efficient burning of heavy fuel oil. The Wärtsilä-Sulzer RT-flex96C, and other low-speed marine diesels like it, represent the pinnacle of large-scale engineering. They are not designed for quick acceleration or nimble response. They are designed for relentless, long-duration, high-efficiency power delivery. They turn the world, slowly and deliberately, one massive, low RPM rotation at a time. The next time you see a colossal container ship gliding almost silently across the water, remember the immense, slow-turning heart beating within, a marvel of engineering designed not for speed, but for something far more critical, enduring, efficient power. The machines that move